So before we actually find the electric field, let's plot out the point 3, negative 4, 3. Here I have 3 in the x-axis, negative 4 in the y-axis, 3 in the z-axis. And that's what the point looks like. Over this I've superimposed the diagram that we came up with earlier and what the electric field looks like for this half line, so we can intuitively get a sense of what the electric field may look like at this point. We can see that it's not going to be purely in the row direction because we're above the line. So it's fair to estimate something on a diagonal like this through the point. I'm going to apply Coulomb's law almost exactly like how I did for the infinite line of charge, in that I'm splitting that continuous half line into little infinitesimal portions of dq and summing them up with integration rather than discrete adding to find the electric field. The problem I have right now is that I don't have dq and r and a hat r, but we can easily find those pieces just by using our intuition and some geometry. So here in the diagram I can see that, well, I just took a piece of this half line, call that dq at this point 0, 0, z prime. Notice the prime notation again, as that's the source. And I find dq just like how I did for the infinite line of charge, multiplying rho l by dz prime. Again, dz prime, because I need to find a little bit of this q, so I must multiply by a little bit of z prime. Over here I found rho equals 5. The reason I did that is because I want to solve this question with cylindrical coordinates. So I have 3 on the x-axis, negative 4 on the y-axis. So 3 squared plus 4 squared gives me 25. The square root of that is 5, giving this hypotenuse, which is also rho. The convention I use is rho phi z. I found rho in the previous slide. Z stays the same, regardless of Cartesian or cylindrical coordinates. Now, this phi bit I've kept as 0 just because this point, the point of interest, and this dq point are on the same plane. So, I could have stuck to convention by keeping this x equals 0 and finding the angle that goes all the way around to this point. But because this point and that point over here, the dq, are on the same plane, and because I will subtract these 2 points to get the position vector, it doesn't matter what I give phi, because the phi components will cancel when I subtract these 2 points. I'll show you this in the next slide. So here I'm finding the position vector r, which goes from here, this dq, all the way to this point over here, 5, 0, 3. So coming from dq to 5, 0, 3. You can see here that the phi components with this convention, so the middle piece over here, will cancel regardless of what you give them, because these are both on the same plane, so they'll both have the same phi components. Now I can simplify this statement over here into this over here, 5, 0, 3 minus z prime. You can work out how to find the magnitude over here, and the unit vector is simply found by multiplying the direction by 1 over the magnitude. Now I have all the components of this dE. I have dq, I have r, and I have a hat r. Plugging in all the pieces we had solved for previously into this statement, you get this statement over here. And that is the key to solving this problem. Essentially, all the hard work is in this statement. Everything else after this is just calculus that you're applying from first year and second year. So here I have dE, and to keep things simple, what I'm showing you how to do here is, well, you can write dE as a rho component, a z component. That's all this vector is. I have a rho component over here and a z component over here. So when I take this integral, I'll have a rho component and a z component when I solve it. Based on that, I'm going to split up this integral into 2 parts. First, I'll rewrite it. This notation is easier to work with. And here I've split up the integrals. So here, all of this is in the rho, and all of this is in the z. I'll rewrite this again to make it more clear. All you have to do now is solve this integral. All of that goes in the rho direction. And you have to solve this integral, and all of that goes in the z direction. And here you go. That is the final solution. Don't forget your units of newtons per coulomb. I've left it here in terms of rho L, and you can easily solve this by hand, which might not be so easy, but it's just mechanical work at the end of the day. All the hard work and conceptual thinking really went into finding the parts dq, r, and a hat are. After that, it was just integration. And you can get your calculator to do this for you. One example would be the HP50G, which can do such integrals. Thank you. I'll see you in the next part for part C of the same question.